Okay, let's dive into this explainer. Today, we're going to completely transform the way you look at shapes, space, and literally the physical world around you. We are taking a journey straight through the fundamental building blocks of geometry. We'll level up from basic one-dimensional borders all the way into two-dimensional spaces. And as you'll see, we're going to discover how some surprisingly simple rules govern everything from the sports we play on the weekends to the abstract algebra equations we write on a chalkboard. It's going to be a lot of fun. To kick things off, let's look at this setup. You have probably seen this 100 times, right? Maybe during the Olympics or just at a local high school track meet. We've got athletes assembled at the start of a 4x100 meter relay race. But notice something right away. They are not starting at the same line. The runners in the outer lanes are stationed way ahead of the runners in the inner lanes, and yet the finish line is exactly the same for all of them. This staggered starting position continues all the way out to the outermost lane. So it begs a very natural question. Does the stagger give those outer lanes an unfair advantage? I mean, are the inner lanes kind of getting the short end of the stick here? It's a real-world mystery that plays out on televisions globally. But to actually solve it, we can't just guess. We first need to upgrade our understanding of mathematical dimensions and exactly how we measure the space those runners are covering. Here's our roadmap for the explainer today. 1. The racetrack mystery. 2. The magic of pi. 3. Leveling up to area. 4. Slicing up circles. And finally, 5. Visualizing algebra. Okay, section 1. The racetrack mystery, understanding 1D borders. To figure out why those racetracks are staggered, we need our most basic tool. The absolute foundation of this is the perimeter. For any given shape, its perimeter is simply the total length around its border. The source material provides a brilliant way to visualize this. I want you to imagine a tiny little insect going for a walk around the border of a shape. It never turns around, it just keeps walking straight forward until it returns to its exact starting point. The total distance that tiny insect travels, that's the perimeter. If it's a square with sides of length A, the perimeter is just 4A, simple, straight, and totally rigid. Section 2. The magic of pi, moving to curves. But here's the thing, the real world and our racetrack isn't just made of rigid, straight lines. We have to transition away from straight, predictable shapes like squares and cross over into the wild realm of curves and circles. Think about what happens if you double the side of a square. Its perimeter doubles too, right? The ratio of the perimeter to the side is always perfectly fixed at 4:1, no matter how massive or microscopic that square gets. So the crucial point is that a circle acts the exact same way, just using different terminology. For a circle, its perimeter, which we call its circumference, compared to its diameter, is also fixed. The source calls this the C/D ratio. Whether it's a tiny point in your pocket or the entire equator of the Earth, that C/D ratio never, ever changes. Since ancient times, people realized this ratio was fixed, and we gave it a pretty famous name, pi. We often use approximations to measure it in our daily calculations. You probably remember the fraction 22/7 or the classic decimal 3.14. But remember, these are just approximations. The true nature of pi is actually much more fascinating than that. Listen to this. As our source notes, and I quote, "The digits of pi go on forever with no visible pattern. Pi cannot be written as a ratio of two integers. Such numbers are called irrational." This is a complete mathematical wildcard. Unlike a neat fraction like 1/3 that repeats in a nice rhythm, pi has absolutely no repeating pattern whatsoever. It is an infinite, chaotic string of numbers that somehow perfectly represents the symmetry of a circle. And this brilliantly illustrates the answer to our racetrack mystery. Let's think back to those runners. The track is built of straight stretches and semicircles. Now, on the straight stretches, everyone is running the exact same identical distance. But on the curves, the runner in the second, third, or outermost lane is running on a semicircle with a much larger radius. And because circumference is tied directly to that radius through our constant pi, a larger radius literally means a longer physical distance to run. So the stagger doesn't give anyone an unfair advantage at all. It mathematically compensates for the longer curve. Because of that stagger, everyone truly runs exactly 400 meters. Mystery solved. Section 3. Leveling up to area, entering 2D space. Now that we've mastered 1D perimeters and curves, we're officially initiating our dimension upgrade. We're moving from the perimeter, the line around the outside of the shape, to the area, the actual two-dimensional amount of space occupied inside it. Let's move to and see how this builds by discovering the area of a triangle. Look, We don't just want to blindly memorize formulas here. We want to see the underlying logic. If you take any triangle and duplicate it, creating an exact congruent copy, you can fit those two pieces together perfectly like a puzzle to form a parallelogram. Since we know a parallelogram's area is just base times height, and our new shape is made of two identical triangles, a single triangle's area must be exactly half of that, 1/2 base times height. It's a shape-shifting visual puzzle that proves the math right before your eyes. Which leads us directly to a really beautiful and surprising theorem from our source text. A median of a triangle divides it into two triangles with equal area. Let me explain. A median is just a line drawn from one corner straight down to the exact midpoint of the opposite side. Because you split the base exactly in half and the height remains identical for both of the new sections, the area formulas are perfectly equal. Even though the two new triangles might look completely different in shape, they contain the exact same amount of 2D space. How cool is that? Section 4, Slicing Up Circles. So let's take these brand new 2D space skills and bring them back to the curves we were discussing earlier. We know the area of a full circular disk is pi times the radius squared, but circles have incredible properties of symmetry. If we cut the circle directly in half, reflection symmetry tells us the area of that semicircular disk is exactly half of the full area, 1/2 pi r squared. If we apply quarter turn symmetry, a quarter circular disk is exactly 1/4 pi r squared. You see, we can logically slice a circle's area into neat little fractions just by looking at the angle it creates from the center point. Section 5. Visualizing Algebra, the grand finale. We've covered a ton of ground, but I promise to connect our geometric journey to a completely different branch of math. Now, what's really interesting about this slide is how physical shapes can actually prove abstract algebraic identities. You might remember the classic formula, a plus b all squared equals a squared plus 2ab plus b squared. Instead of just memorizing letters on a page, picture a physical square where each side is length a plus b. If you slice that big square up based on those lengths, the areas of the smaller pieces perfectly equal one a squared block, one b squared block, and two a times b rectangles. Geometry physically proves the algebra. The math isn't just symbols, it's real physical space. Which leaves us with this final thought, straight from the sources Think and Reflect exercises. We know a median divides a triangle into two equal areas, even if they end up being completely differently shaped. So here is my challenge to you. Can you physically divide one of those triangles using straight cuts into pieces and then rearrange those pieces to exactly cover the other differently shaped triangle? Think about the physical reality of the math theorems we just explored today. It's like a giant puzzle. I'll let you ponder that one until next time. Thanks so much for joining me on this explainer.